All right, let's go ahead and kick it off. Good evening, everyone. Thanks for joining us. I see everybody's hopefully putting in their name so we can record attendance. I think we've got this down to a science now. I want to welcome everybody to this evening's presentation. We have Dr. William Bally. It goes by BJ Bally, Dr. Bally, however you'd like to address him. He is a research assistant professor at Texas A&M University. Whoop, I have to get that in. As an Aggie, it's obligatory. So he got his PhD from Michigan State, as you can see on the wall behind him, and did his undergraduate and master's work at University of Nebraska-Lincoln. So Midwest guy that we've got on here. He's part of the Department of Atmospheric Sciences at Texas A&M. And a lot of his research, as he said in his little short bio, centers on the intersection of weather, climate, and agriculture. It's a really interesting place to be. So we'll let you take over and drive. Dr. Bally, you can put your slides up and be sure we can see them.
Okay, let me give that a shot here quick. But yeah, as Michael mentioned, my name is BJ Bally. I'm a research assistant professor at Texas A&M University. I also serve as the assistant state climatologist for Texas. So work with Dr. Nielsen Gammon in the state climate office here at A&M. So before I get started, as mentioned, I'm not from Texas originally. I'm a Midwesterner from South Dakota originally. Spent a little time on the West Coast, but then spent about 8 years in Lincoln, Nebraska, and then about another decade in Michigan before coming down to Texas. So I guess if you want to trace through the schools I've been at, I am a Cornhusker, Wolverine, Spartan, Aggie hybrid. So it's quite a mix at this point. But just getting started. So that's just a little bit of background about where I'm at and how I got to Texas. But yeah, I've been at Texas A&M just a little over 2 years and loving it here in the Brazos. So happy to be here tonight and give this talk about climate and weather in Texas and what makes where we live unique and some of the challenges we might face, historically and going forward. One just prime example is pictured there on the screen. So those are 2 pictures from this week here in College Station. So the one on the left was just about an hour ago outside my window. Now it's dark. It's kind of nice here though. We're up on the 12th floor of the O&M building here on campus. So we've got a nice view of town. My office happens to face north, so I get nice sunset views. So that was tonight, but about the same time on Tuesday, if you look at that, that's from ground level out by Highway 6 here in town, but we had dust blowing in from the western side of the state. So same week, 2 very different skies about the same time. That's going to be one theme you're going to notice a lot during tonight's talk is variability, and sometimes in pretty short order. So where there events can happen where we experience extremes back to back pretty quickly. By the way, can I just get a quick thumbs up that everybody can hear me okay? Okay, great. I thought I was coming through, but just wanted to check. So tonight, what we're going to be doing is kind of a lecture. So we're going to go through and cover the climate of Texas, all the way from what a local climatology is, talking about space and place, and what makes each location unique. We'll also talk about natural variability. So what makes these variations we see from year to year? What forces that variation within the natural system? So we're not talking about anthropogenic climate change or man-caused climate change at that point. We're going to talk about those natural varying components of the system and then put the recent climate in context. So what we've experienced in the last several decades versus the paleoclimatic record and what we've experienced in the more recent observational record. From there, we're going to move into climate change. So what we've already observed in Texas and what's projected to happen through the 21st century, and really kind of talk about it from more of a physics-based approach, breaking it down into physical components and what forces change. So, and then also talking about some questions about how you can investigate climate change on your own and some questions that are important to ask. We'll also talk briefly about extreme weather in Texas, which is a favorite topic of everybody in my office is talking about extremes and in Texas, as well as droughts and floods. At the end, I do want to talk a little bit about CoCoRaHS. Some folks may have heard about that on here, but that is a volunteer organization all across the country that takes daily weather observations for rain, snow, hail, basically different forms of precipitation. And a lot of folks that have been involved with Master Naturalists Also have gotten involved with CoCoRaHS over the years. So if you weren't aware of the program, I'd like to make that available and just chat about it. And then at the end, we have time for discussion, or if folks would like, can demo a few tools. So we have a lot to cover, but if we get through it, hopefully we can walk away with a decent understanding of Texas climate, and hopefully I do my job all right. So let's get going. So when we talk about Texas and we talk about climate, one way that when we talk about the first climatologists and how we know what we know about climate in Texas is what happens with the ecosystems, what ecosystems are present, what plants, animals, insects, birds make up the environment that we live and exist in different parts of the state. Those are shaped by the climate. So those normal rainfall events, what the normal temperature is, those annual cycles of heat, sunshine, rainfall, snow, and ice in some parts of the state, those are what shape what plants and animals are present on the landscape. So there's always been an intricate connection between climate, vegetation, and what folks see on the landscape. So we often talk about climate in terms of ecosystems. That's one way I'm going to talk about this tonight. The other is in the context of geography. Funny enough, my PhD is actually in geography. It's not in meteorology. So climate also hangs out in geography departments sometimes. So that's how I got into here. So it's nice being back in a meteorology department, like where I got my start. But we also, especially in geography, talk about climate, ecosystems, plant geography, what plants are present when and where. So that's going to be governed by one thing, your average conditions in a place. So you often hear climate talked about in terms of averages. What is the average temperature? We've seen, in the US, 1 point something temperatures of Fahrenheit of temperature increase since the beginning of the 20th century. Those are mean values, and departures from those are important. So even knowing what those mean values is important because it describes the average of the climate that we exist in. What is that 50th percentile? What's that middle value? What can you expect? The extremes, we can also do that from a probabilistic standpoint, but in a way they're what you get. You don't necessarily expect them, but they do happen. We do a lot of modeling to understand the probabilities of extreme events occurring. And extreme events are often what are the most impactful, what affect the ecosystem, what affects our managed systems, our natural systems that generally create shocks to the system are those things at the edge of the distribution. So even though they're kind of an outsized or, under a small portion of events, so a small sample size, those extremes can have a really distinct impact on climate and what lives and what's present in it. So really you have to be able to tolerate those extremes and, thrive in the mean. So when we think about this in terms of plants, so Texas creates a unique set of circumstances just because it's such a large state and has such a diverse range of climates and ecosystems. So plants in Texas, especially out west, do need to be drought tolerant. Drought's a common feature all across our state, even down in the southeast corner by like Beaumont, Orange, on the Sabine River, a place where it usually rains 70 to 80 inches of rain a year. Last fall, they had crevices in the ground opening up so large cattle were getting stuck. And because it was so dry, magnolia trees were dying. So even in our wet, humid, murky places that we don't think of as having drought, we can see it here in Texas. So they have to be drought tolerant everywhere, but out west, droughts can last years. So they have to be particularly drought tolerant in the western part of the state. They do have to be heat tolerant. It's hot in Texas all the way from the southern border all the way up through the panhandle at different times of year. So, our state average record high is 119 degrees. And so we have to be able to tolerate quite a bit. And you can see that those high numbers, you can reach triple digits in any part of the state for a good chunk of the year. Even along the Gulf Coast where it's really humid, you can crack those triple digits sometimes. So they do have to be able to tolerate heat. And we used to say cold in the north. So cold tolerant, particularly in the north. But you'll notice that's crossed out. Folks that were living here in 2021 went through Winter Storm Uri and saw that cold can get all the way down to the southern border, and it can last that way for quite a while. We'll talk about that event in context later today. It is an extreme example, but interestingly enough, it's not our most extreme that we have in the instrumental record in Texas. So we'll kind of put it in context of where that fits. But in Texas, that's a pretty tall order for plants. So they have to be tough. So you have to be drought tolerant, heat tolerant, and cold tolerant, and that applies to the people here too. So pat yourselves on the back. It is a hard place to live in. One thing about understanding climate, though, and where we exist is where it sits physically. So Texas has a couple different things that make it pretty unique in terms of the climate it experiences. We're parked down here at the southern part of the continental United States, kind of at the top of the southern third of North America. And, we're sitting right next to a big body of water. So the Gulf of Mexico, it's a pretty warm body of water. It's not that deep. So it's that creates a big governor on Texas climate. Also, you notice the mountains out here in the western part of the state that extend down into Mexico, up into New Mexico, up through Colorado. Those also create a block. So that creates dry conditions out west because they starve it of moisture coming in from the Pacific. We're also open to the north, so open to the Great Plains, so we can get those Arctic blasts coming down from the north. So really, Texas is a constant tug of war between tropical air and cold Arctic air, and we're kind of in the south end of the shooting gallery in between. The Great Plains of the United States are one of the most active severe weather places in the locations in the United States, mostly because they have access to an open tropical ocean and the Gulf of Mexico, and then an open Arctic Ocean with the Arctic. There's not a lot of mountain ranges between the Gulf Coast and the Arctic Ocean up here in Canada to block the air. So you can really get source air from anywhere, and that creates the perfect mix for volatile weather, severe weather, and a lot of extreme events. So that's physically where we're sitting. So when we look at that, when we look at weather, we often talk about climate in terms of temperature and precipitation. They're two of the longest observed variables that we have. Some folks think that, intuitively would think that sunshine, or was it sunny, cloud cover, would be the observation we've taken the most long, even in manually observed records. It's actually rainfall. So did it rain? Those are some of the oldest records that we can find, are carved on, cuneiform tablets, and they're translated as rain records. So we've been doing this as long as humans have been able to write down what they're seeing. Assuming it probably even goes back further, we just haven't found the records yet. But if we look at what happens with precipitation across Texas, one of the biggest things, the biggest controls on the climate and the environment is the presence or absence of water. And when do you have water? When is the water there? When is it not? It also governs temperature. So we're going to start with precipitation. But when we look at Texas and we look at what's happening annually across the state, you'll notice on that map that there's a pretty steep gradient. You'll notice a lot of cool blue colors on the right. And by the time we're out at El Paso in the west, those colors are getting pretty dark brown, orange, red. So those hot colors are low rainfall totals. Those cool colors are high rainfall totals. If we saw some purple, like in the Olympic Peninsula in Washington, you're going to see those be bright pink, or, those colors are not on our part of the map. But that's kind of the range we deal with in the continental United States, from areas that receive less than 4 inches on average in places like Death Valley in California, to areas that see over 160 inches of rainfall a year in the Pacific Northwest. So we have quite a range. In Texas, we range anywhere from, approximately 8 to 12 inches out by El Paso, to anywhere from 60 to 70 to 80 inches in the southeast corner. So we have quite a range. But if you go east to west across the state, we see a big drop off as you head from east to west. So that's a big control on our environment. How much rainfall we get on the annual basis. But one of the big things too is, when does it fall? And part of that is a very distinct seasonal pattern in precipitation and what triggers it. So if we start in January, we're going to go through each month of the year here with precipitation and look at the same map. The color scale does change, so this isn't proportional, but it's relative to each month. So if we look at January, we see kind of that same pattern we saw annually. Precipitation, we see that east to west gradient, those high totals along the eastern border on the Sabine River, and the lowest totals in far west Texas and the western panhandle. So that's pretty normal for winter. That is pretty close to our annual precipitation total as well. As we go through the year, though, February, we see this same pattern. March, we're seeing these magnitudes go up as it warms up. A warmer atmosphere can hold more water, but this pattern we're seeing is largely holding. As we go to April, we're progressing to spring. We still have this gradient, but you'll notice some of these bars are expanding. These contour levels are getting wider. And as we settle into summer, you're going to notice there's fewer and fewer contours on the map. This is breaking down. We're still seeing the values with each month pick up, but we're seeing this penetration further into the state with these higher totals, and we're seeing less of a gradient. By the time we're into June, this is when we start to see those really hot temperatures in the last part of the month. The dog days of summer where it's cloudy or where it's sunny for 3-4 weeks straight. The wind doesn't blow. If you get rain, it's just because of a pop-up thunderstorm. We see that precipitation gradient we usually see across the state break down because the main mechanism that we see causing that rainfall is different. During the cold season in Texas, we're sandwiched basically between the polar jet stream and the subtropical jet stream. So the jet streams are these fast-moving areas of air aloft. About 250 hectopascals will be the pressure level they sit at in the atmosphere, or way up there in the stratosphere where jetliners like to fly. These things are what largely steer large-scale weather systems. So during the cold months, Texas, we're in between these two. So we're in the shooting gallery. Things are moving east to west. We get progressions of weather systems, but we're far enough south that in the summer, that subtropical jet expands north. And often on the news, you'll hear the term under the dome, under the heat dome. Well, that's what that is. Once you're under that subtropical jet, we're in we'd refer to as a tropical atmosphere. And what that means is there's generally not a lot of weather systems, a lot of movement of large scale weather systems. If you see weather, it's due to convective thunderstorms, and that tends to be smaller scale. So those can happen anywhere in the summer in the state. Some areas are more common than others, but we tend to see the amounts really even out. So by the time we're into July, most of the state, except right along the Gulf Coast, where a lot of that climatology is going to be affected by tropical systems, hurricanes, anywhere in the state can get roughly averages anywhere from 1.2 to 2.4 inches of rain during the month of July. And that's because of those thunderstorms. So if you look at this on a time series, like a diagram of precipitation, where we're at in College Station, most of the eastern part of the state has a dual peak, one in the spring, one in the fall, and that's where we see most of our rainfall. We actually dip in the summer. So peak summer, we see less rainfall than we do in the spring. That's very different from where I'm from in South Dakota. Farther north in the Great Plains, we get almost all of our rainfall in about a 3-month period in the summer. Otherwise, it's very cold and very dry. Texas, we don't have that. So as we move through summer, same thing. So into August, you're really seeing that tropical signal in the southeast part of the state, but you notice that holding with the rest of the state. You'll see some isolated areas where you see these blue bullseyes up in the panhandle. Those are larger individual rainfall events that are big enough to skew the climatology, but those would have been associated with a very large thunderstorm system at one point. So as we move into fall, though, you're going to notice this gradient start to return. And that's more this average condition that as that polar jet stream starts to push south, that subtropical jet stream starts to push south, we start to see more movement of weather systems from east to west. It's not isolated convection anymore. And then we see that gradient set up as we move into the fall. And by the time we're back to midwinter, we're to a distribution that largely looks like that annual maximum value or that annual average value of precipitation. So for Texas, we do get quite a bit of rainfall, but it depends on what time of year and when we're getting it. And so if you see in the summer, you get most of your rainfall out in the west, that's when you're going to see a biomass accumulation. Same in the panhandle. And then if you have a really wet summer and you don't have a wet winter, that can create a lot of fire damage or risk later in the next spring. So there's drawbacks to everything, but that is what we're doing in terms of precipitation. Now, if we go to look at temperature, we're going to see another gradient, but it's almost the opposite direction of what we see with precipitation. So really, Texas climate is getting pulled both ways, from east to west with water and north to south with temperature. So if we look at what happens in January as opposed to precipitation, this is looking at the daily maximum temperature. So most of the state is bouncing anywhere from 46 to 50 degrees Fahrenheit up there in the north for average maximum to down by the time you're in the Rio Grande Valley, even in January, you're still in the mid 70s, 74, 77. Everywhere's a little bit in between. But you'll notice this largely follows how much sunshine you'd get at that given time of year. So southern parts of the state have longer days, tend to get longer solar periods of insolation. They stay warmer. The farther north you go, same thing. With precipitation, though, or with a minimum maximum temperature, minimums, you also know about the same pattern. It is a little more modified. Actually, what you're seeing there is the influence of the Gulf of Mexico. So it keeps air along the coast more humid, more moist, so it can't cool off as much. That's when you get fog. You're hitting the dew point. And until that air loses some moisture, it can't cool off anymore. So that's why this area, if you look at the southeast corner of Texas, really jumps up with those high values for the minimums in winter. So that's the influence of the Gulf. Now, if we go to summer, though, you notice that pattern is completely gone. This is minimum temperatures. And you'll notice there is a little, I mean, if you look from deep south straight up to the panhandle, there is a gradient, but you actually see more of that east-west pattern set up that we see in the summer. And what you're seeing there is largely reflective of being under that heat dome, not having that movement of weather systems. So every day, most of the state is sitting here baking. You'll notice even some of the hottest temperatures are along the Gulf Coast, deep South Texas, where we would expect them in Big Bend. But you'll also notice that since these are minimum temperatures, this is nighttime. So you're also seeing that Gulf influence. Dallas, the DFW area also pops out. That's a heat island. So that is man-made surface concrete holding on to that temperature. So there's one way detectable with these average minimum temperatures. You can see humans' impact on the environment already, just looking at the average temperature data. We're making that area warmer on average by being there and having built infrastructure. That minimum is important, but if we look at, hang on a second. Yeah, that's right. Okay, we didn't change the value on this. So this is indeed right, the minimum. This one is actually the maximum temperature for July. And you'll notice that same pattern, except the heat islands are gone. During the daytime, you generally don't see urban heat island effects pop out because the surrounding area can be just as warm. But you'll notice that temperature across the state is really uniform, except just right along the Gulf Coast there, or in some high altitude areas in far west Texas. Most of the state can hit those really high temperatures during midsummer. It's not just the Rio Grande Valley, Big Bend. Anywhere in the state can hit high triple digits during that peak of summer because we're under that subtropical jet, and the air is just literally sitting here, heating up and cooling down with the sun and not getting much added to it except what blows in off the Gulf. So that is a pretty stagnant time of year. But that is kind of the range you'll see. So in the winter with temperatures, we see that north-south gradient that largely follows the sun. And then in the summer, it's more of where is the location of that jet stream and where do you see this weather track? So sometimes in the summer, that jet stream will park over the panhandle and they'll be very wet while the rest of the state is really dry. That's what we saw in the summer of 2023, when a good chunk of the state, especially the southern 2/3, was in pretty gnarly drought most of the summer. The panhandle was actually getting a lot of rain. They had a good crop year, but that's actually what set the stage for the really bad fires we saw the following winter. So in one way, it was a real blessing. In other ways, it set up for a really bad situation a few months down the road. But with that range, Texas, we can see everything different times of the year, different times of month. It'll vary, but be ready to kind of exist at the extremes, whatever you do. So what we were talking there is actually about that average condition, what we can expect, what the temperatures look like in the winter and the summer, what rainfall looks like throughout the year. But there are other things than just what that average condition is that affect climate. One of those things, often gets put under the title of climate variability and change, like the slide says. Climate variability, though, is anything that can really cause that climate to vary from year to year, month to month, place to place. Those are things you may have heard of. Some of them you may have not. So the first one on that list, most folks in Texas have heard about it, is ENSO, or El Nino Southern Oscillation, or El Nino La Nina in common names for referring to events. What that is, we'll talk about that more in depth in a few minutes, but that's a cycle in atmospheric pressure and results in sea surface temperature changes in the equatorial Pacific, and it has a pretty big impact on the weather in the southern parts of the United States, particularly in winter. There are also other modes of variability, such as like the Atlantic and Pacific multi-decadal oscillations, so things that happen over the course of decades. These long-term climate oscillations that we have. In the Atlantic Ocean, the Pacific Ocean, again, largely large-scale pressure patterns and temperature responses, but those can have impacts on weather a long ways away from where those temperature changes are happening. So we look at that as well. Some more impactful events, volcanic activity, that changes. There are times where the Earth is a lot more active. There's a lot more volcanoes erupting. There's times like now where it's been relatively quiet globally. That can vary, as well as solar activity. The sun has cycles, so sometimes it outputs a little more, sometimes it outputs a little less. Sometimes it's going to keep gaining brightness until it starts expanding, gets red, and eventually burns out. But it does vary on human timescales, so that is something we need to look at as well. There's also changes about atmospheric composition. So what is in the atmosphere in terms of gases? What is, being put out by plants, being uptaken by oceans, being put back into the atmosphere. Also stuff in the atmosphere. So it's not just gases, whether they're human caused or natural. There are objects in the air like aerosols, dust, soot, particles that also can affect our climate. Also changes in the land surface. So what we do on the land. So my background is more in agriculture. So depending on if you till your dirt, if you do no-till, if you plant cover crops, that land surface can have an impact on the climate, especially when you do it on a large enough scale. Same goes for cities, you name it. So if we change the presence of the land surface, that's going to change our fluxes of water, change our fluxes of energy at that location, and that can change the climate. And if we look at longer periods, so we just covered this in my physical climatology class this semester, but changes in the Earth's orbit. So these occur on the order of, every 30,000 to 100,000 years. Changes of where the Earth sits in the plane of rotation around the sun, where's the tilt of the Earth's axis varies over time, how elliptical or round the orbit is around the sun, that can vary. And each of those has an impact on climate over the period of thousands, tens of thousands, hundred thousands of years. So all of that is part of the equation of what constitutes climate variability and change. So there's a lot of pieces. There's a lot of moving parts. So we're going to go through these a little bit piece by piece and break these down. One of the first ones we're going to talk about, and probably you've heard more about in Texas, is El Nino, La Nina. So El Nino is one part of that equation. So that is when this area in the equatorial Pacific, so on each of these graphs, kind of dead center in that map, you'll notice there's the hotter colors, the warm colors are in that area. So these are showing sea surface temperature anomalies. So blue areas are areas where it's cooler than average. Red areas are where it's warmer than average. And the darker the color, the bigger the anomaly. So not every El Nino is the same, but one feature they do all have in common are anomalously warm waters in the equatorial Pacific. It has to be over an area. There's a couple different places you can look, but they generally have to be defined as 0.5 degrees Celsius above that long-term average over a 3-month period. Once you meet that threshold, congratulations, you now have an El Nino. Cue the old Saturday Night Chris Farley skit. But that is what constitutes an El Nino, is when that area in the equatorial Pacific is 0.5 degrees C warmer than that long-term average. La Nina is the exact opposite. If it's 0.5 degrees cooler than normal, then we have a La Nina. But El Ninos and La Ninas are not all created equal. They're not all the same. So if you look at this, we've got some years like 2016 where that was a really severe El Nino. It was really warm in the equatorial Pacific, pretty similar to the last winter we had with 23-24. That was also a El Nino year, and it was pretty strong. Some years are pretty weak where we don't see a strong event like 2005, 2019, 2007. The impacts don't scale proportionally with strength. Sometimes a weak El Nino can have really bad impacts, or a weak La Nina can have really strong impacts. Where I was at before in the Great Lakes, in the northern tier, there are other things that govern the climate more than the equatorial Pacific, but everybody likes to be tied to El Nino and think there's some predictability on it. So in the Great Lakes, folks always talked about, oh, La Nina winters are really bad. They're going to have a lot of ice cover and snow. Well, when we plotted the data, that's actually true for weak La Ninas. But by the time you're at a really strong La Nina or a really strong El Nino, you saw pretty much the same response. It was wet and warm. So it wasn't a linear response there either. But even close to here, it's not a one-to-one relationship. There's other factors that modify the climate than just El Nino, but it tends to tip the scales one way or another. So where we're sitting currently, this was last fall. We saw us going into a La Nina. So you notice those blue colors are popping out on the map there. That was when the last El Nino really ended. La Nina years, by contrast, you'll notice this is the flip of that first map that you saw. That's when those tropical areas are cooler than normal. Same thing, like 2011 was a very severe La Nina. La Nina impacts are a little more predictable for the southern part of the U.S., and I'll break that down as to why. but I'll give folks, I usually cue the room and ask for a question when I do this. Oh, I saw go green on the chat, go white. So, yep, go Michigan State. But I will just say to the room, if 2011 here, you see that's probably our most severe La Nina that we have plotted here. What happened in 2011 that was the most drastic thing that year, starts with a D, is drought. So La Nina years tend to be drier than normal, particularly in the winter when we'd be seeing recharge. And so they are often associated with drought. The last severe drought episode we had running from 2020 through early 2024, and some parts of the state are still in it, was associated with a triple dip La Nina. So 3 La Ninas back to back to back. And that sets up a dry period. That was also evident in the 1950s when Texas saw probably the drought of record for most of the state, where they're saying it didn't rain for 5 to 7 years. In some places, that was fairly true. I mean, it rained off and on, but not much. So the 50s were really dry. It's actually why we have the Water Development Board in Texas. But yeah, the La Nina years tend to be dry and cool, but not all La Ninas are the same. So I don't blow my next couple of slides here. I'll get going before we get caught up here. With El Nino, there's kind of a little moniker that we can use to remember that. So El, or extra liquid Nino. So during the cool season, so that would be usually October through April. I guess on this one it says, November to March. From November to March on this one, you generally can see above average precipitation when you have El Nino in Texas. So like last winter, 23-24, that's when we saw the drought really see widespread relief across a lot of the state. It was an El Nino year. We saw warmer than normal conditions. We don't see as strong of a temperature signal with El Nino. I'll show that in a bit. But the precipitation signal is pretty strong. So we tend to see wetter than normal winters with El Nino. Contrast with La Nina, or less agua, Nina cool season precipitation, we tend to see lower than normal precipitation, particularly along the Gulf Coast in Texas during La Nina years. If we look at what it means for temperature, though, El Nino cool season temperatures do tend to be cooler than normal during El Ninos, though this really is more associated with more rainfall, more cloudy days. It's not really associated with a lot of large scale movement of air systems keeping it cooler. It's more key that it's cool and wet and we're not getting as much sunshine. As opposed to that big red area you see across the Pacific Northwest and the northern tier, that is because of the location of the jet stream during El Ninos. They tend to be under a big ridge and they tend to be much warmer than normal during El Ninos. So that's why where my parents are now, and I went to high school in Oregon, during El Nino years, the skiing is bad because it's too warm. It all falls as rain. If we look at La Nina temperatures, that's also this is more of a predictable response here in Texas, is we do see warmer than normal temperatures. And that is tied to, again, that location of that subtropical jet, it not being north of us during El Ninos, but it is during La Ninas. And we see those corresponding temperatures as a result. So La Ninas tend to be warmer than normal during the winter. During the summer, there's not a real strong signal. There is one clue there in Louisiana and Mississippi where you do see those big departures in terms of precipitation. So in Texas, we don't really see much of a signal, but in Louisiana and Mississippi, we do. That has to do with hurricanes. So tropical activity is something that is also pretty, in the Gulf of Mexico, is something that's pretty intricately tied to ENSO. So El Ninos tend to result in a lot of wind shear across the Gulf in the summer, and that tears hurricanes apart before they can form. La Ninas tend to result in a very still Gulf, and there's not a lot of wind shear going on, and so hurricanes tend to grow more readily. They don't get torn apart by winds as they form, and we tend to see more rain hurricanes during La Nina warm seasons. So that's why over in Louisiana, Mississippi, you see that uptick in precipitation. The only climate division in Texas that really shows that is that far south, the lower Rio Grande Valley, for the same reason. They tend to see more hurricanes. The mid-coast, it gets washed out over time, but they can get hit more too. But that's the main feature of La Nina, El Nino for summer weather for Texas. In terms of, we're going back to this one, this is La Nina. So this is cool season precipitation. So just getting at that point again, we tend not to see that rainfall in the cool season with La Nina. During that warm season, again, hurricanes. So coming down to Texas and how this has been changing over time, though. So we talk about that variability piece with El Nino. With El Nino, we tend to see cooler winters, wetter conditions. La Nina, we tend to see those drier winters with warmer temperatures and more active tropical seasons. But how has this started to change over time? So when we look at Texas, you're going to see two things on your screen here. One, you see a bunch of squiggly lines for time series showing temperature, and then you see a map on the right showing trends in temperature across the state and how those vary. So what those different squiggly lines are different data time series. So HADCRUT, GIS temp are gridded temperature series from satellite data and weather observations that are merged together to come up with a spatially coherent data set. These are global data sets. Historical plus RCP 8.5 is the historical time period plus a little bit of the future projections from the last set of climate models that went into the IPCC. And then that Texas number is the 9-year rolling average of observations all across the state. So those are weather observations. So one is averages of grids over Texas, the other is an averages of stations. That's why there's some difference in the variability of those lines, are different grid resolutions and gridded data versus station data. But the one thing they share in common is they all largely track with one another. You see there's year to year, there's some ups and downs that don't exactly follow. And that is some variations in what went into the data set, what was detected, what was not. But overall, that upward trend is present in all the data sets, especially since 1980 across the state. That's where these really converge. And that's not just here, that's across a lot of the countries. We see that signal really take off in the 1980s. That's the statewide average for Texas. So from 1900 to about now, we've seen roughly 1.6 to 1.8 degrees C in temperature increase over that time period. If you fit a line through those, that's about what that change would be since about 1900. That's pretty close to the national average for the US, a little less than the northern tier where I'm at, where we've seen most of our warming in the winter. But if we look at from 1975 to 2018, that's what the map on the right shows. We should probably update this here soon. But we show that that temperature increase isn't uniform across the entire state. There are some counties in the far northeast corner of the state where they've seen very little change in that overall annual temperature and not as much and sometimes in the summer, they've even come down because it's cloudier. There's less sunshine. But overall, most counties and most places in Texas have seen temperatures go up over time. This is more marked in central Texas, deep south Texas, and far west Texas, where we've seen increases on the order of 0.8 to 0.85 degrees C just in those last couple decades. So there has been quite a bit of warming. It's increased in pace since 1980. And when we look at it from different areas of evidence, different sources of data, we largely see the same picture. So there's consistency there. So when we look at not just the temperature as an indicator of climate, but we actually look at what makes that temperature. So going back to what we talked about earlier, composition of the atmosphere, land surface, all those different things can have an impact on what makes up a daily temperature. So when we think about daily temperature, most of that incoming solar radiation, so it's a sunny day, passes through the air, hits the land surface, and a certain amount of it is reflected back into space. If there's clouds, those clouds absorb some of that radiation, emit some of it right back into space through reflection, and then the radiation is then re-emitted down through the atmosphere, so some of it hits the ground even on cloudy days. But radiation comes in, passes through the air, bounces off clouds. When we think about where we live in the low levels of the atmosphere, air is mostly heated and cooled by the ground and plants. It's not directly by solar radiation. It's actually by the ground being warmed by solar radiation, and that re-radiating out of the ground to heat the air. So that's why there's some lag between sunrise and when temperatures start to tick up. That's primarily through that conduction mechanism. And also then it is also transpired, through transpiration from plants, evaporation of water, that also moves energy and moisture, doesn't necessarily respond to a temperature change. So that variation can be a lot of the what matters. So what's on the ground where you live and what the plants are like can govern how that air is heated and how you exist and what you feel. So one of those things that actually makes a nice example of this is area from where I went to high school or close to it in Oregon, this is the Columbia Valley, Columbia River Gorge, so northern part of the state, right on the border with Washington. So if you look at the river in the middle, that north side is Washington, bottom side is Oregon. This is at the upper end of the Columbia River Gorge near Umatilla, Oregon. There's a big military depot there. There's also a lot of agriculture in the valley because we're near the Columbia River. In the Northwest, most of our rain falls in the winter, not the summer. Summers are pretty dry and warm. They're actually very pleasant, but agriculture there is thus very dependent on irrigation and reservoirs and rivers. So here, right next to the Columbia River, you've got a nice annual supply of water that doesn't wax or wane much. There's a lot of hydro dams, so it's pretty predictable. So you see a lot of irrigated agriculture. That's what those little circles on the map are. So that top map is made using something called NDVI. That is a sensor on satellites that look at near infrared data. And so those are bandwidths in the near infrared frame wavelengths. So we can't see it, but it's near infrared. So everything emits a certain bandwidth of that radiation, and it's related to temperature. If we look at NDVI, that product derived from that, that gives us an indication of how green a landscape is. So if it has a high NDVI, it's usually green. We can associate that with vegetation. If it tends to have a low NDVI, it's either desert, dirt, there's nothing growing on it, could be asphalt. But even land with plants, it can vary quite a bit. So plants do not all equal one in this case. So those dark circles have high NDVIs. It's kind of those pastures, rangeland in between. Those are going to be more at your 0.3. So there's vegetation there, but it's not as lush. It's not doing as well. The water is not treated here. And then, roads have really low values like 0. So that presence or absence of vegetation is going to govern how much water is coming up from those locations due to that vegetation health. Where you see that high NDVI value, that vegetation is healthy, it's clipping along, you've got good evaporation, good transpiration, and it's pulling water from the soil, moving it up into the atmosphere. Areas where you see that lower value, there may be plants there, they're doing this, but there may not be enough water there to make those plants real healthy. There may not be a really dense plant population, so it's more just soil evaporation and the soil surface is dried out. Those areas are not transpiring as much. When you look below, that's an image taken from another sensor that looks at that land surface temperature. So not how hot the air is, but how hot the surface of the land is. If you notice those areas with high NDVIs, they have some of the lowest land surface temperatures, save the river itself. Those areas like that big square area in the middle of the screen, that's the ordnance depot. That's the military installation I talked about earlier. You notice there's not irrigation. It's a lot of open dirt and fields. They have a lot of bunkers there. You'll notice there, land surfaces are 20 to almost 30 degrees Celsius warmer in some of these really exposed areas versus these irrigated fields. So that's just one real direct example of how drastic that land surface in a small area can affect your temperatures. So do that over a large enough scale, and you can see how that would scale up to a regional climate change or a national climate change signal if you have enough land surface change. The Dust Bowl in the 1930s is a good example of that. Large disturbance of topsoil in the southern and central Great Plains. A couple of years of drought, failed crops, kept tilling it up, topsoil blew away, and then you didn't have anything growing for a couple of years. That's where we'd set all the temperature records that are still largely holding to this day across most of the central part of the US. Those maximum high daily records were mostly set in the 1930s. And that can be attributed to the Dust Bowl and farming practices. So this is a more micro scale look at this, but I like how that is a way to show that. If we look at Texas in terms of what temperatures do, in terms of that average daily or minimum temperature, over time, what you're seeing on this map or on these plots are a time series of that statewide average. So each of those dots is the average statewide daily maximum temperature in a year from 1900 or 1895, right before 1900 through 2023 on this plot. On the right there, you're seeing the minimum temperatures averaged over the entire state. So you notice there's two patterns. There's some things that are alike and there's some things that are different from these two plots. If you notice the one on the upper left, that's maximum temperatures. So some things to note over time with maximum temperatures in Texas, they have gone up since about 1900. If you look at the center of that line, that moving average line, we were looking at statewide average temperatures of about 77 degrees Fahrenheit. At the end of that line, you're looking at between 77.5 and 78. So we have warmed. There's also some other interesting things when we look at this over time that are worth note. So if we look at the past from about 1900 till about 1960, there was quite a bit of variability. Those dots go up and down quite a bit from year to year. If we look at the 1960s through 2000, or really about 1980, but even on this one for Texas 2000, you notice there's not a lot of variability there. We saw about 2 or 3 decades where year to year, things didn't change all that much. Things were pretty stable. That made for good farming, made for good water resource planning, and that was all well and good. But since about 2000, with those high temperatures again, and you see this in precipitation as well, you've seen that variability really pick up again. So when we talk about it being, man, it seems like 2 years ago, we just had way too much water. Now we don't have enough. You're not crazy. Nobody's tricking you. That is what's happening. The variability has really picked up statewide in the last couple of decades. When we look at maximum temperatures, that maximum temperature is going to again be determined more by that plant health, by what those surface characteristics are like, how much of your energy is being partitioned into what we call sensible heating. That would be something that heats up the air, like what it sounds like, radiation heating up the ground, warming up the air, sensible heating, versus latent heating, which is more due to the evaporation of water or transpiration of water, and it doesn't result in an apparent temperature change. It's the movement of energy through water, not through heat. So when I say latent heat, that's water movement. Sensible heat is actually warming something up, is what it sounds like. So that summertime maximum is really going to be determined by that ratio of latent to sensible heating. So when we're in drought conditions, more of that is going to go into sensible heating. You'll notice those highest values that we saw in before the year 2000 in Texas are really concentrated in the 1930s and then again in the 1950s. So those are two eras of really severe drought. If you look at this map right here, our time series in the center part of the screen on the right, you'll notice that since about 2000, we've definitely seen that variability pick up. Our hottest year on record in Texas was 2011. It's still holding on to that with the drought record, but it's gotten very close. But overall, we have seen warmer years in the last couple decades than we saw in the years prior. We've also seen that temperatures pick up. When we look at the minimum temperatures, it's a little bit of a different story. You'll notice before 1980s, that was really consistent. We didn't see a lot of variability year to year. We didn't see, big spikes, big up and down, decade to decade. Most of that increase we've seen has been since about 1980. That is an idea that the air is now holding more moisture because the overall atmosphere of the globe is heating up more. It's not a local or regional change. And if you have a warmer globe, a warmer atmosphere, it can hold more water. So that raises your dew point. If your dew point goes up, you can't cool off as much at night. And so really most of the increase we've seen in those nighttime temperatures has occurred in the last couple decades. And that is actually more of a warming signal than we've seen in the associated daytime highs, where it's going to be more governed on how wet it is or how dry it is. That annual signal with minimum temperature is going to be a more reliable indicator. If you look at daily temperature records and which stations are setting records, we are setting quite a few maximum temperature records every year, but we're really blowing the minimum, like high minimum temperatures out of the water. So high overnight temperatures. If you look at midsummer, you probably see a lot more records for those broken than high daytime temperatures. I mean, we have been seeing that in Texas and a lot of other areas. Just to put the last couple of years into context, statewide, not just looking at one number, these are 2 drought periods. So this would have been looking at June through August of 2023. That was the second warmest summer on record. 2011 is the warmest still, even given this last year. But this was out of 129 years at the time. 2023, like I mentioned before, was not that droughty up in the Panhandle and across Oklahoma. That's probably why it's the second warmest. The southern part of the state, if you look there, starting at El Paso, counties in between were second warmest, but everywhere you see that dark, dark red, that's the warmest summer on record for those counties. So everything in the southern 2/3 of the state had its warmest year on record during summer of 2023, not in 2011. The reason 2011 really takes the cake, that orange area is probably second warmest for most of those counties. But the northern part of the state was really dry, hot that summer and dry that as well. That was one unique feature about that. It was affected the whole state, not just not the southern 2/3 or the northern third. It was everywhere. So 2011 is still the drought record and still the warmest summer on record for much of the state. Two things that did different though was precipitation. So precipitation, like I mentioned, was well above average in the northern part of the state. It was well below average in the southeast corner, but other parts of it, it wasn't all that dry. That's one thing we're noticing with these summers that we're seeing these high temperatures, droughty conditions, flash drought because of high evaporative losses. It is actually still raining more frequently, more often. It's just evaporating quicker. So that's one thing. With the summer of 23, we saw decent precipitation over a lot of the state, just not really in that southeast corner. 2011, on the other hand, we saw low precipitation across the entire state. So the character of droughts that we're starting to see is also starting to shift. It's not just, it's not raining, it's not cooling off at night, it's staying too warm, and we're getting more evaporation. So you can see that in data, even when you look at more fine time scales like weekly or monthly data as well. To talk about the last fall and early winter into context to put it how warm that was. This is January 1st to October 14th, 2024. So this would have been actually last winter through early fall of 24. Things were still quite warm. If you look at this map, what these are temperature rankings. So a lot of the state saw its warmest period on record for that first 3/4 of the year last year. Top 5 is where you see those dark reds. Oranges are top 10s. Whites are anything below a top 10, so kind of those middling percentiles, and vice versa. If it was cold, they'd be purple. That was something we saw across a lot of the region, was warm temperatures for the first half of 24. If we look at minimum temperatures, though, this is kind of illustrating that point I talked about earlier. Maximum temperatures are there, so still pretty warm. Top 5 for most of the state, top 2 in a lot of cases, but those minimum temperatures were warmer than 2011. That dark crimson would be, it's the warmest for that period on record. So a lot more stations are just not cooling off at night. So that's really what's forcing a lot of the temperature change in the last couple decades. It's not really getting warmer during the day that often. In the winter it is, but annually it's the daytime temperatures aren't changing as much. It's just not getting as cold. So that's kind of the takeaway from those slides. Precipitation, similarly, 2024 was not that dry of a year on record, though we were still seeing drought impacts in a lot of the state carrying over from years prior. But yeah, it was pretty dry in far deep South Texas, but most of the state it wasn't that dry, but we were still setting those temperature records, like I scrolled back to. So that's that minimum for precipitation. Most of those had a pretty middling year, but it was still hotter than average. And so we saw a lot of water stress in crops, even though we were still getting rainfall. Going back to this series, just to look at it again, so to put that in a little more context, when we look from 1900 through early 2020 or early 2000s in Texas up through 2023, we see overall that temperature has changed. We've also seen the variability change over time. The variability we're seeing now is not unprecedented. Before 1960, the variability was pretty similar year to year. The only difference now is we've got a stronger background climate signal on top of it. So it is getting warmer on average over time. And now that we've ramped up that variability again, it seems even more drastic. Same thing for those minimum temperatures. That variability is not really changed, though. And you even look at now, that variability really has not changed because the amount of air or moisture at the air at those low temperatures doesn't change on average all that much. Unless you've got a big movement in weather systems day to day, it can change a lot. But on average, it won't. But you've noticed now that background trend, though, with those warming temperatures, you've seen those temperatures respond in kind, even though we haven't seen that major change in variability that we've seen with the high temperatures. So those are some takeaways to how temperatures changed over the last couple decades in Texas and moving into the future. So I think after this slide, we're going to take a break for about 5-10 minutes. I'll see what time it is when I finish up with this slide. But then we're going to move into climate change, what forces climate change, and then what the projections for Texas and the southern region are like for Texas. So this is looking more at extremes than the last slide. I'm going to go back here for a second. This is talking about that average daily maximum temperature and average daily minimum temperature. So if we look at what was the hottest temperature during a given year during the summer, that pattern's a little more amplified. That cold pattern's a little more amplified. So we're going to talk about extremes here for a minute. So looking at that average hottest monthly temperature, so June through September, that's when we see our hottest temperatures every year, is going to be in peak summer. We will not see them in winter. That's just physically impossible. But for now, barring, a comet hitting, a nuclear winter, and something really catastrophic, trying to keep it light here, but barring all that, you would not see that hot temperature change all that occur outside of summer. The average hottest temperature in Texas has varied over time. If we look back about 1900, it was bouncing between 100 and 96, 97 degrees Fahrenheit. We saw over the next couple decades through the 1930s, the Dust Bowl, through 1940s and the 1950s during that really bad drought. Those hot monthly temperatures were really high. It had jumped up 3-4 degrees on average. You were seeing your averages usually be 103, 104, 102. Those average hottest daily temperatures during the year, or hottest monthly temperatures, really ramped up. Then we saw that period in the 1960s, things cooled off, that variability went back down. Over time, things cooled back down. But since about 1980, things started creeping up. And since about the year 2000, in the 20 teens, we've caught back up to where we were in the 1930s, 1940s, 1950s. So it'll be interesting to see over the next decade if this pattern holds, if it steadies out, if it could reverse. That's not likely, but time will tell. But how things have changed over time for the hottest month we're seeing in the year, when we're seeing the hottest temperature hasn't changed all that much, but we have seen that variability shift, and it's ramped up to actually higher variability than we even saw back in 1900. Actually, I'm going to see, I actually forgot. There's a laser pointer tool. Can people see the laser on the screen now that I'm dragging it? Awesome. Usually I'm pointing or have a laser pointer so I can point at these things. Doing it on Zoom is a little bit different, but now that I can do this, this is great. So now we're seeing we saw higher variability back here in the early 1900s for that hottest maximum temperature or month during the year. We saw that kind of reduced variability. There was a warm one here, but overall things calmed down. Things were cooler, more moderate climate. Since about the year 2000, we've seen that variability return higher than it was really even before with those high summer temperatures. Here's 2011 there. There is not 2023 on here. 2024 is not on here as well, so I need to add them. 2023 would have been just below that 2011 dot over here on the right side of the graph. So those are the hottest summers on record so far for Texas. What we're likely to see in the next few decades is more of that. So if you want a preview of what the next 10 to 20 years look like, even though the climate model signal is weak at that point, look at the last 2 or 3 summers, and that's probably the more likely condition. When we look at cold, though, we've seen a little bit more of a solid trend in the cold temperatures, but we can still get cold, as 2021 proved. So looking at the bottom right now, we see these are the coldest temperatures, coldest month on average during a year for Texas. So if we look back about 1900, right in 1900, that winter was very, very cold. That's the coldest it's ever been on a monthly basis in Texas. So back in 1900, it was below 0 for average temperature when you took all the stations in the state and averaged them together. That is the only month that ever came in below 0 for the state of Texas. So, and this is in Fahrenheit, not Celsius. So that was really cold. But overall, the average condition back then, the average for the state was bouncing between 12, 16 degrees Fahrenheit. Over time, we've seen this gradually go up. The variability, again, in the 1960s to 80s really took a back seat. We've seen it come up somewhat, but we're not seeing as many really cold winters as like we saw in the 20s, 30s, and 40s. It still does get cold, as we saw in the 1980s. And again, in 2021, we can still see these really massive cold air outbreaks, but they're just not happening as often. So they can still happen, but we're not seeing them every year like we were back in the 1920s, 1930s, 1940s. Most winters, it's just not getting that cold. And if you look at this right side of the graph here, we see this like bunching up of temperatures. Since about the mid-1990s through now, there's just been a lot more winters where it's just not getting as cold. So it's not getting as cold on a monthly basis. But February 2021, it still can. But so what that goes to show is that even though we're seeing a warming climate where it's not getting as cold as often in the winter, it doesn't mean we don't have to prep for the cold, because it can still happen, as people saw in 2021. And when utility companies, city, municipal, state governments don't take those preventative actions for cold, when we get caught off guard, we can still see really drastic impacts. But folks who lived through 2021, who hadn't been here for 30, 40, 50 plus years, might have thought, man, it has never been colder than this. And for their experience, that was true. But it has been colder in the past. So you can have disproportionate impacts, even if it's not the coldest event on record. So with that, going to take a little break. I think everybody's on Zoom tonight. I think that's correct. Nobody's in a central meeting location.
Right.
So it's about 8 o'clock. So meeting wraps up around 9. So how about we take a 5-minute break and come back at about 8:08, 8:09?
Perfect.
And we'll get started onto climate change, the climate system, and what we can expect going forward. So thanks everybody so far, and hopefully we'll have some time at the end for some questions too. So see everyone in a couple minutes. So looking at so far we've covered climate. So what is that mean condition? You know, what we can expect from climate, what we kind of get at the extremes. So what is kind of the most maximum and most hostile climate that we can expect at a location, and how that varies over time, and how we've seen that change across Texas. We'll talk a little bit more about those extremes in general here at the end, but we want to talk a little bit about the climate system as a whole and what forces change, and what we can expect going forward from here. So some basic rules of the climate system. So you can think about it like a bank account. You know, deposits are in the black. If you take too much out, you're in the red. You know, if we accumulate too much energy in a system, it's going to respond. If we take too much energy out of a system, it's going to respond. Most of the time with the climate system, the energy is almost exactly equal to the energy out, basically to within 1% in a given year. Some years are a little bit warmer than others, some are a little bit cooler than others, but that radiation budget will almost come out to zero on an annual basis. Over time, if more energy coming into that system, more deposits coming in, that climate is going to warm up. Your balance is going to go up. So not always a good thing in this case, but if more energy comes into that system than goes out, it is going to warm. Over time, if more energy is going out than is coming in, as we've seen in the geologic past with ice ages, those are times where the radiation budget of the Earth was negative over a long period of time, and it cooled off, saw expansion of ice sheets. If we look really far back, like hundreds of millions of years, there's a period of Earth's history where it's hypothesized the entire globe, except for little tiny areas around the equator, was completely covered in ice. And that was because of a positive feedback mechanism. It just kept feeding back on itself and growing. But over time, there was enough change. Volcanic activity picked up, more gas went into the atmosphere, and it melted off. And then that's never happened again to that extreme, but we have seen a lot of ice ages over geologic history. So those would be areas where we saw the climate cooling. Not what we're seeing now, where we're seeing warming on a pretty broad scale over a pretty rapid period of time, if you consider it from a geologic standpoint. But those are some basic rules. So thinking about it like a bank account, if more comes in than goes out, you're going to see the climate warm up. Vice versa if it goes the other direction. All right, we're back here. So when we consider the future climate, we have to ask a couple of different questions before we start down that road. This is what modelers have to ask themselves even before they start writing code or start formulating a model. When we think about the future, we have to ask what will be in the atmosphere. So what are, you know, how much is going to be in the gas from human activities? So things like carbon dioxide, sulfur dioxide, aerosols, how much of that will be there? How much volcanic stuff will be there? Just what will be in the atmosphere? We have to ask that question. Given what we think is going to be in the atmosphere, we have to understand and think about how much of that will affect the global climate system. Some things are going to cause a positive change in terms of, when I mean positive here, you're going to retain more energy. There's going to be more coming in than going out. There's going to be some changes that are a negative, that hide some of that climate change, that balance it out. How much each of these individual components will balance with one another, and we need to understand those individual components and what they contribute. Another thing is, what are the local consequences of those changes going to be like? How would that affect people in a local area, not just a global area? And then on top of all this, we have to consider natural variability. So what is that natural variability within the climate system, and what can we expect? And then those changes all on top of one another, each other, are what we'll actually get. So those are four pretty big areas that we have to look at when we consider what the future climate is going to look like. If we look at historically what we have observed in terms of climate change, what those forcings are, I know everybody's looking at a screen. Hopefully the graphs are coming through clear. That is one nice thing about doing it over Zoom. We don't have a tiny screen in front of the room, and I'm interpreting for everybody. But what we're seeing on the screen right now is a series of graphs from a scientific article that was looking at climate change, observed warmings, and how much of this was driven by emissions from human activities. That included both warming and cooling aspects. So this breaks it down in a couple of different ways. So if we look at attribution studies that look at relative warming from 2010 to 2019 relative to 1850 to 1900. So relative to the last half of the 19th century. So 1850 to 1900 is what we're comparing this to, and this would have been the last complete decade, so 2011 to 2019. On that graph, just to the right of that gray bar on the left there, that gray bar is the observed warming. That error bar on top is the wiggle room due to depending on which data set you use to calculate it. So that's kind of our observational uncertainty. On there, it's depicted as about 0.5 degrees Celsius. I'd say that's pretty accurate on a global scale. When we look at the next chart over to the right, you're starting to see some reds and blues where my pointer is now. This is studies that looked at attribution, so what is causing climate change. So not looking at radiative forcing on a component basis, but overall a larger assessment looking at attribution from particular groups. So looking at all human influence, that's this plot where my cursor is now. We've seen about just over 1 degree Celsius worth of warming, give or take about that 0.5 degrees. If we just looked at warming, that would be from well-mixed greenhouse gases. That's things like methane, nitrous oxide, carbon dioxide. That warming would actually be greater than what we've observed. It's estimated that about 1.5 degrees Celsius worth of warming would be the average with a larger error bar. But even on the lower end of that observation, you're still at total human influence. So even if some of these cooling things don't matter, we'd likely have seen more warming than we have. So it suggests there's something else going on. So that's the impact from greenhouse gases. They will result in climate warming and more than we've seen. So you see that blue bar there, that's other human drivers. We're going to take a more nuanced look at that in a second. But those would be human activities that are actually resulting in a net cooling. So those activities grouped together result in a cooling effect that obscures some of the total human contribution of climate change from greenhouse gases. Just for context, folks often ask about solar and volcanic activity and internal climate variability. Those are valid components of the system. That's what those error bars there to the right of that blue bar on this central chart show. But those error bars show pretty much your whole range of possible involvement of those. So for solar and volcanic activity over this time period, it could be about 0.2 degrees C, give or take 0.1 degrees C either side. So it's pretty much a wash when you average everything together. So solar volcanic activity has not been a major forcer over that time period. And then internal climate variability, so that would be everything else we talked about, like ENSO, PDO, Pacific Decadal Oscillation, so those large-scale teleconnections, climate variability modes, that's about 0.5 degrees C, centered around 0, so 0.25 degrees plus or minus. So they really wash out. So when you talk to folks and people bring up solar volcanic activity as potential drivers of climate change, they absolutely are. They're not incorrect. But the magnitude of that change over the same time period is pretty small compared to the human drivers. So going beyond that, the one on the right, so this was part of a review paper. If folks have done some grad school, read scientific articles as part of a college science class, or just read them, because you're a concerned citizen and enjoy reading scientific articles, this is what's called a review paper. So they went out and looked at a lot of different studies and kind of aggregated the results here to kind of give a state of the field. So that's the type of paper this graph was sourced from. We love those kind of papers because they do good literature reviews for us. When you're not writing a paper, if you find a good review article, it can give you a really good background on the field and state of where things are at. Anyway, back to this though. The graph on the far right of this is done from a bunch of radiative forcing studies. So this is not an attribution study. This is actually models where they break down individual components and look at the contributions of carbon dioxide and methane and nitrous oxide, different gases, and they parse out the different warming contributions of each of them. So this is a more zoomed in look at those human drivers over here, these bottom three. So if we look at carbon dioxide, that's the one we hear the most about. So industrial processes, driving cars, agricultural processes, all of that contribute carbon dioxide. If we just isolate that alone, that's responsible for about 0.75 degrees C of warming just by itself, give or take a little bit with the error bar. If we move over to methane, it's not as common of a greenhouse gas as carbon dioxide, but it punches above its weight. So it has a higher warming potential. That is sourced from a lot of natural systems emit methane. Melting permafrost is a big source. The deep ocean is an area of methane. So is rice cultivation is a big source of methane, as are feedlots. So agriculture is a big component of this. So stuff I study, we are really concerned about methane and nitrous oxide emissions. So this is something I've looked at a fair amount. But methane does warm about 28 times more than carbon dioxide unit per unit. The amount of methane that's been emitted over that time period would be estimated to be about 0.5 degrees C of that warming. Nitrous oxide is a really potent greenhouse gas on the order of about 200 sometimes more strong than carbon dioxide. We don't emit a lot of it, but when it is emitted, it does have a pretty potent effect. Agriculture is probably one of our biggest sources of nitrous oxide. That's actually what my PhD looked at. Wasn't nitrous oxide, it was nitrate leaching. So nitrogen going out through the bottom of soil profiles with rain in corn and soybean systems. So here's where we crack jokes about the most Midwestern PhD ever. Spent 7 years looking at rain and corn and beans. So I talked with a lot of farmers about the weather and how it affected corn yields and corn prices. So exciting stuff, but it was good for the time. I enjoyed it. But we do talk a lot about nitrogen, but nitrous oxide is also a part of that system. So if you have waterlogged fields, rice cultivation, if it's paddy rice flooding, that is part of the cultivation process. When you get that, nitrogen cycle is leaky, it leaks out nitrogen. If it's in an anoxic state, a lot of it goes out as nitrogen oxide or nitrous oxide. Through a gas form. So that's where a lot of that's coming from. So, but really when we add all that up, that's about 0.15, 0.2 C of that warming. Halogenated gases are from a lot of different industrial sources, natural sources, but those get grouped into about the same amount as nitrous oxide on itself. You'll notice there's some blue bars here. So we do have some different things. There are different nitrogen oxides than just nitrous oxide. Those are also largely agricultural and natural systems emitted. Different nitrogen oxides are larger particles. They actually cool a little bit. So about 0.2 to 0.3 degrees C of that warming has been canceled out by those different nitrogen oxides. So we've really canceled out the nitrous oxide components. So balancing a little bit here, but there is still a lot more red than blue. Volatile organic compounds, which are from agriculture, industrial processes, chemical reactions, and carbon monoxide, that's responsible for about 0.25, 0.3 degrees C of warming. So another pretty substantial one there. This is one chart that probably needs to be updated in a few years about what I'm about to talk about next. So we're talking about masking global warming here. One of the biggest components of that over the last several decades has been sulfur dioxide. Sulfur dioxide, one of the largest sources of that is shipping diesel, shipping fuel. If we think back to 2020, 2021, if folks are involved in the energy industry or were just paying attention to the news and heard the discussion, or the climate sphere, we were talking about it too, was they lowered the amount of sulfur dioxide that was permissible in shipping fuels under international regulations. So ships are running cleaner now, which is generally a good thing. It's better for the surrounding environment. You're not getting as much environmental pollution, but we're also taking out a lot of sulfur dioxide that we are artificially pumping into the air for decades. Sulfur dioxide is a really powerful aerosol for cooling. It absorbs a lot of solar radiation. So we have now stopped adding that to the atmosphere. And so some of the massive warming, the big spike in global sea surface temperatures over the last 2 or 3 years, some of that could be attributable to this change in shipping fuel and altering the radiation budget over the shipping lanes. So a lot of what you're seeing on this in terms of cooling may go away. It's in the troposphere, it's not very long lived. It will precipitate out over the course of a season or so. So it's what was there is no longer there. Sulfur dioxide is what we get worried about is when it gets up into the stratosphere, which can happen with things like asteroid impacts, large volcanic eruptions like Pinatubo in the 90s that altered weather for a few years. If this stuff gets up into the stratosphere, it doesn't rain out very quickly and it can stay up there a long time. And then you can see broad scale cooling. That gets into the idea of geoengineering and something we're not talking about tonight, but that is, you may hear that bantered around in the discussion as well. So aerosols are a big concern when it comes to climate modeling and climate forcing. And there's something we understand surprisingly little about as a scientific community. So there's a lot of research actually here at Texas A&M. There's a big chemistry group in the department here that works on aerosols and environmental chemistry. So active area of research, and there's been some big changes globally in that sulfur dioxide emissions that people do. And we're starting to see some rebound from that. So that could be part of what you're seeing when you hear about global sea surface temperatures over the last couple of years being way out of bounds. It could be part of that. We were obscuring some of that warming with what we were putting back into the system. Organic carbon can be another aerosol that tends to absorb a lot of radiation. They're dark particles, so that can cool some. Ammonia can be agricultural source, can be a little bit of cooling. Black carbon would be like forest fires, things like that. Burning carbon material, that tends to be a warming process because it also emits carbon dioxide, more particulates, not good things. Land use, reflectance and irrigation. If you add water to a land surface, make it more lush, that will cool things off. So that's a slight sink. And then over there on the right, that is aviation contrails. So if we want to get into the whole chemtrail debate at some point, that is the total influence of aviation contrails. So it is measurable, but nothing compared to the gas emissions that we put out. So the takeaway here, this is kind of like hitting everything over the head with a rubber mallet, but humans do have an impact on the environment. We are responsible for a lot of the warming over the last several decades and last century through greenhouse gas emissions. There is a natural component to it. Either way, regardless of the proportion that's natural versus man-made, we have to adapt and be resilient in that environment. So that is part of that. So when we talk about aerosols, those are a big deal. There are some more interesting optics that can happen. So just thinking about radiation budgets and some unique categories, these are some nice imagery. One is showing dust off the west coast of the United States, blowing off from the west coast of California. The other one on the right there are actually what we call cloud punch holes. You don't see them very often, but that is thin layers of ice clouds, so cirrus clouds high up in the atmosphere. And when planes go through them, it actually super cools the water fast enough that it turns that ice to liquid and it leaves a hole. And actually where planes are pretty long lived, they can carve big areas in this cloud deck. So that's just showing how optics and what's in the atmosphere can affect things on even pretty short time scales. So in areas where you see below those hole punches, you'll see warmer temperatures, you'll see some sun poke through, and it'll be a nicer day. So if that happens in, like, say, the winter time. So that's just two examples there. So looking into the future, so we're talking about what's in the atmosphere, what those different drivers are, black carbon, carbon monoxide, nitrous oxide, that whole list. When we do climate modeling, one of the things that forces a climate model is called the emission scenario. So emission scenarios are what they sound like. They're conditions that describe the gaseous components of the atmosphere over time. And scenarios are likelihoods, situations, stories, if you will. So each different scenario, which you're seeing on the screen here, each of those lines represents a different emission scenario, is a different story about how humans might evolve or change over the 21st century. So these ones start in 2015 with the last IPCC run out to 2100. Some of the models actually run out to like 2300, run longer, but we'll just talk about the 21st century tonight. Each of these different stories is an attempt to capture, Potential futures for humans. Are we going to be a more united society globally? Are we going to be more regional, more isolationist? Are we going to see more global international trade, more intense local trade, resource intensive versus technological development? All these different scenarios are tried to be captured in this. So the different scenarios we really talk about here, a lot of the ones you'll hear about more often are kind of a business as usual scenario. That would be SSP 5 or 8.5 for the old RCP logo. That's this top line here. A lot of people will argue that scenario is too aggressive. And with some models, it is. Some GCMs simulate total ice sheet collapse under this scenario, and that sends models just skyrocketing. So with this model, this scenario may be a little aggressive. SSP3 is a more resource-intensive development, more regional, not as high-tech, but not as demanding on resources. What I would consider the most likely path we're on is somewhere between those two lines right now. This one's probably a little high. This one's probably a little low. Kind of your low emission scenario that most people talk about is SSP2, the old RCP 4.5. That's this line you're seeing here, this yellow one. These bottom two are interesting. So those are low emission scenarios. The 1.9 is specifically the emission scenario we would have to follow to meet the Paris Accords and keep global climate change below 2 degrees C as a whole. We've already overshot that one. So this one is largely not realistic, but it's a good modeling exercise. The one above it is also tied to that. It's a little more realistic, but SSP 126 is probably not likely either. So mostly what we'll be talking about tonight are these three. So kind of our low, medium, and high emission scenario. The likely futures where you track them all will likely fall somewhere within the range of these three. So that's this wide range of variability we get to deal with. Easy, right? No, it's a heck of a problem, but we'll get going here. So it's not just carbon dioxide, though. Different types of development can result in different types of gas emissions. So we think about carbon dioxide as the big one. That's what drives the boat, and that's true. But with these different scenarios, so SSP5 is a very intensive development scenario, high industrial energy, and eventually these outputs kind of peter out. One, because technology's improved. Second, we've largely exhausted the easily extractable carbon-based fuels. So we've used everything we can easily access, the party's over. So that's probably not going to happen there. SSP3 is more regional, more conflict present future, so there's not as much technological development. There's more resource-based development. So if we look over here to the right, there's graphs that show methane and nitrous oxide. If you look at that, SSP3, those are way up. And that's because of heavy agricultural development and all arable land essentially being used over time. With those other ones, the more technology savvy one, 8.5, SSP5, you figure some of that would have curtailed because of technological advancement. That's an assumption the modelers are making. If you look at these lower ones, these are basically decreasing over time from now on. So methane drops under 245, same with nitrous oxide, same with sulfur dioxide. So again, these are all things that affect that overall warming or cooling or wetting or drying you get from climate models. How is that radiation budget presented? Does it balance? Those are the key questions climate modelers ask, whereas if, say, you're using a model like this to forecast weather, which weather models and climate models are pretty similar. The big difference is weather models are more focused on short scale, like time physics and microphysics of clouds. That's more important for convective development, severe weather. You can't model that over time as much. It gets really chaotic, and it's not as big of a concern for climate over time. But what is a more of a concern for climate models is how are we representing the energy budget? Like, where is energy coming in? Where is it going? How's it being partitioned? That's the big difference between meteorologists and climatologists, where we spend our time asking questions. But each of these has a component that'll affect that radiation budget. Moving into what that looks like, feeding those different pieces together. This is a time series of global surface air temperature change relative to, again, late 1800s, early 1900s. That gray line on the left there, that's the observational record. The light shading you see is the uncertainty from the data source being used. You'll notice that narrows slightly as we get to the more recent decades. We're more confident in our observations. But most of those data sets agree. You see that upward tick in temperature over time. I mentioned volcanic eruptions and cooling. That's what happened here. So in 1991, Mount Pinatubo erupted in the Philippines, put a lot of sulfur dioxide way high up into the atmosphere, and it actually cooled global temperatures by about 0.2 of a degree for the next 2 or 3 years. Some ways that affected weather here in the US. Texas, not quite as much, but Florida, Hurricane Andrew in 1992. That hurricane season had some major connections to that cooling. They've attributed it to that. Also, the spring floods in 1993 in the upper Mississippi Basin, the upper Missouri Basin, the Dakotas, where I'm from, that was a pretty epic spring in terms of rainfall and flooding. That's all tied back to partially to that volcano that blew up in the Philippines. So that's that, and shows you what an event like that has an impact on temperature globally. So moving up, things kept warming back up, and 2015 for these is where the projections take over and we quit ingesting observations for these models. So from here on out, we're into scenario land. We've got our high scenario, our middle scenario, our low scenario, and then our kind of fantasy land scenarios at this point down here in the lower right. But what you'll notice is over the next couple decades from here on out, these lines don't diverge much. And so what that is warming has inertia. The climate system has inertia. It kind of has momentum. It takes a while to get things up to speed, but once they are, it carries for a while. Temperature tends to lag gas emissions. So what you're seeing in these climate models is really the warming as a result of the emissions that have accumulated since the start of the Industrial Revolution, not what we're going to emit necessarily. That impacts us later. So if we look over the next couple decades moving forward, we're seeing global warming, not a lot of divergence among these scenarios till about 2050. That is when the changes in these different scenarios that were shown here start to take effect. So after 2050, we're going to see largely divergent futures. But up until then, we're largely in what we call the adaptation space. We can do a lot of changes. We need to make changes as a society, as a group. However, the actions we've already taken, there's a price to be paid for them, and that is the climate's going to keep warming regardless of what we do. An interesting modeling exercise that's often done is an abrupt cutoff of CO2 emissions. It takes 30, 40, 50 years for things to start to even out after a large period of emission and a large imbalance. That's looking at climate sensitivity. So up through 2050, we can expect probably globally continued warming from about 2015 on the order of about another degree Celsius if we take the middle road there. From there on out, the emission scenarios really start to take over. If we were going to look at SSP5 here, by the end of the 21st century, we were looking at global temperatures about 4 to 5 degrees Celsius warmer than what we experienced historically. SSP3, a little lower than 4 degrees Celsius, and our low one puts us just a little below 3 degrees Celsius. That doesn't sound like a lot when we talk about our day-to-day fluctuations in temperatures, but on an annual basis, that is quite a bit. To put this in context, all of our observed climate change going back to like the last glacial maximum, so the peak of the last ice age till now, it's estimated that temperatures were anywhere from 10 to 12 degrees Fahrenheit cooler than they are today at the peak of the last ice age. So if we convert that to Celsius, that's about 8 degrees Celsius. So you're talking about, 10,000 years of climate change in roughly 150 years, to put this in magnitude of what we're projected to see. So not trying to sound doom and gloom here. There's ways we can adapt and plan and be resilient, but it is a big problem, and it deserves to, be shown the respect that it's due. It's a big issue. But either way, if we look at the bulk of these scenarios, kind of where that shading is at, you're looking at by the end of the 21st century, globally, we'll have to deal with anywhere from 3 to 5 degrees Celsius of global warming. So that's the most likely future scenario going forward. What that means in terms of things like global sea level change, there we're looking at things like land-fast ice. So Greenland and Antarctica are really key places to look at for this. You may think the Arctic, and that is one place to look as well. Arctic sea ice, though, in the northern hemisphere is largely over water. So it changes the radiation balance of the thermal regime quite a bit, but it's not going to contribute that much to sea level rise beyond thermal expansion of water. Land-fast ice, though, if it's over land, where you see large glaciers like Greenland, the ice caps, and then Antarctica, that's the stuff we're concerned about for global sea level rise because it's not in the water already. If you think about it in terms of sea level rise, I think there was something that popped up in the chat here. apologies, said this, different groups producing different models. Oh, yeah, so So yeah, these are different modeling groups. Sorry, I didn't make that clear. So where we have like different things on these graphs, these different bars, those ranges are usually the ranges of the different models. So they're different modeling groups, not different models from the same modeling group. All these together as a whole went together to what informed the Intergovernmental Panel on Climate Change. And there are more climate models out there than what are in these. These are a subset of, I believe, about 30 different GCMs, so general circulation models. I've seen some papers that compare as many as 200 models. So there's a lot of models out there. But these are 30 models that a large consensus of scientists got together and feel are pretty credible. So that's what's being presented here. So these are different models in the range of variability. So do models include the effect of loss of snowpacks? Yes, they do more now. So that's part of what I was talking about earlier. Some models, like what are in here, they have now like ice sheet instability on them. The models didn't used to be able to simulate that. So some of those, with incorporating new processes, has resulted in some uncertainty of some really hot models. But overall, there's more fidelity. More of those processes are being simulated now. So that's something that's a bit of a moving target. The technology has changed, but more models are incorporating things like that. Okay, yep, no problem. So this is just looking at sea level change. So given those projected changes in temperature, how different are the projected futures in global mean sea level rise? So this is 1 meter globally. So that'd be a pretty big change. So at the top of that SSB5, a lot of ones are looking at about a meter to about 1.8 meter or 0.8 meters with 3.7, about 0.5 meters with 2.5 or 2.45. That is quite a bit of change. There's some variation, but either way, sea level rise is something coastal areas will have to deal with. That upper line there is kind of the doomsday scenario, and that would be like total ice sheet collapse of Antarctica, Greenland, basically the globe being completely free of multi-year ice. Most climate models right now don't show that actually happening. Where the Earth becomes permanently ice-free, even under really aggressive scenarios. But there are some models out there that project that. So that upper bound there with 1.5 to 2 meters of rise by the end of the 21st century is a low likelihood, high impact type scenario. Most models don't simulate it. Even those that can simulate it, it doesn't usually get triggered, but there are some where it does. So that is kind of the catastrophic scenario. Moving from there, in terms of temperature, globally, what we're looking at in terms of mean warming, we're going to see the Arctic warm faster than we will see in equatorial areas. And I see my timer is about to buzz here, so I've been talking too much. So these last couple slides will go a little faster, but there are some things I want to get through. So, and with under global warming, temperature is not projected to change the same everywhere. You'll likely see greater changes in the Arctic. We've already seen faster changes in the Arctic. But what that results in is a globe that's much more homogeneous north to south. That changes things like movement of weather systems, can really slow it down. So when we talk about weather systems stalling and blocking and being under the dome, and it seems like it's happening longer, it's because it is. We're generally seeing Arctic warm faster than the tropics. That shallows out that north to south temperature gradient and can really slow down the movement of weather systems. So as we increase that temperature globally, you're likely to see that pattern continue with more amplified changes to poles than the equator. Precipitation is a little more difficult than temperature due to just the nature of simulating it. It occurs at smaller scales that models don't simulate, and it's just a more tricky variable in general. Under projected global warming, Arctic areas where it's cold, where it freezes regularly, are projected to get wetter, and that's because of more precipitation falling as rain, and the air can just hold more moisture. The tropics are a little trickier due to the intertropical convergence zone and how weather systems move. But what we'll likely see is areas that are historically dry are projected to get drier. Areas that have been historically wet, save sub-Saharan Africa, are projected to generally get wetter. So really, it's kind of a feast and famine type scenario. So as we warm, we're likely to see more intense rainfall events, given our thermodynamic knowledge of the atmosphere. but it may not rain as often, particularly here in Texas. That's what we're looking at. I'm going to skip through a couple of these. You've seen some of this before. This is just putting out a notice for an update for the assessment on historic and future trends of extreme weather in Texas. This is a publication that we put out at the State Climate Office, and there should be an update coming out in the next month or two that has some more things about fire weather and runoff from rain and how that might change over time. So that's my reminder timer going off. But look for this. Some of these graphics are from that report, and they've been updated to be through last year, so through 2024. We've seen that one before. So this is just an example of the plots that are in there. So that's that average hottest monthly temperature and then that coldest monthly temperature. And these will have been updated through the last couple of years, so to see how those have changed. I do want to talk about quickly attributing trends to climate change. So when we ask ourselves a question about climate change, how do we know there's a trend? There's three things we need to look at. One, we need to ask ourselves, is there a clear historical trend? One of those things, why we ask ourselves that is, one, humans are creatures of confirmation bias, and I'm just as guilty as anybody. We tend to look really hard, look at things sideways, and tend to see what we want to see if we think it's there. We need to be very objective and look at it. Is there a clear historical trend, or is it in the noise of the observation? What is there? Okay, if we've established there's a clear historical trend, what do models project about a future trend? Are the models consistent? Do the models group together? That would indicate we have a good physical understanding of this change. Okay. Or are they all over the place? It looks like a shotgun spread across a target. If it looks like a shotgun spread, that's a red flag. That's something we need to look at. The models probably don't have a good handle on that process. So that would be something we need to look at there. And then, even if we have a clear historical trend, if our models say there is a projected consistent future trend, we need to ask ourselves, is there a physically sound reason for this trend? Like, is there a physical explanation for what is going on, and should there be a trend? If yes, great, you've checked off all three. If no, we need to do a little more research and figure out why it is before we attribute a trend to anthropogenic climate change or vice versa. But if you've got those three things, those are really important. A last one to really think is, do these magnitudes check out? You know, are the magnitudes of the trends we're seeing plausible? If you can answer those four things, you can probably get it published in a good scientific journal, and you've probably made a pretty good argument for saying there's a trend. So it's not to be glib about it, but those are some things that we have to ask ourselves to be certain about it. So we tend to be pretty conservative on saying if there's a trend in the climatology community, just because we need to meet those bars of proof. If not, it can be suggestive. We can say things are trending a certain way, but we can't say there is absolutely a trend. There has to be a high burden of proof there. Part of the things we can look at, and this is where I'm going to probably skip here towards CoCoRaHS at the end. A lot of our knowledge about future events can be broken down to things like thermodynamic knowledge and dynamic knowledge. Rainfall and temperature are two examples of this that we've kind of consistently used, so we'll use them here. Things we can say about the future, and that's actually what a lot of this Texas report leans on, is more of this thermodynamic knowledge, the way things are. So things that we physically know are true about systems. If we understand how those things change, we can say things about the thermodynamic properties of it. So for example, warm air holds more moisture. We know that is true. We can do chamber experiments to prove that. So heavy rain should increase. That pans out with the observations we have globally. So that's one thing thermodynamically, we understand that's true. That's where a lot of our information in climate models about precipitation comes from, is that warming atmosphere. It doesn't say a lot about the dynamics of it. Another example of thermodynamic change would be what I was talking about a minute ago, is where the Arctic warms faster than the rest of the globe. Yep, that's true. So Texas winter cold should become milder. In general, that's what we see. Cool. Dynamic systems, though, dynamic parts of the equation are the way things behave. So this is where you can get some of that chaotic behavior, some of the extremes that get away from that average. So an example of that would be dynamic information. The maximum intensity of hurricanes is increasing. Okay, we have seen that to a point. So some hurricanes will produce heavy rain longer. Some things we don't know is how Saharan dust and aerosols in the future are going to affect hurricane formation. Is ENSO going to get stronger and shear off more hurricanes? Is that small scale convection within the eye wall of a hurricane going to be more intense or weak? Those are questions that our climate models just can't answer. That's where you have to rely more on our dynamic knowledge to make those leaps. So things about like extreme precipitation, those are harder to predict. So those would be like dynamic models. So another example of that would be Arctic sea ice loss disturbs the stratospheric polar vortex. This is the second part of that upper bullet point that talks about Texas. So if we have more stratospheric polar vortex anomalies due to Arctic sea ice loss, we could see more weather patterns that lead to cold weather in Texas, and they could happen more often. So we may see more events like 2021 in the future, even though they may not be quite as cold as the historic past. That pattern could get more frequent under climate change. So that is kind of what we're talking about when we talk about climate projections. We have to look at our thermodynamic knowledge as well as that dynamic knowledge. Most climate models are good at the thermodynamic part. The dynamic model part is where they've struggled, but we're catching up fast with advances in computing power and techniques. We're able to simulate a whole lot more than we were even 10 years ago. And the models are validating better than they were. So our confidence in our modeling has improved. Still got a long way to go, but hopefully that tonight was a good overview of Texas climate, what we've seen historically, what some of that variability is like, and where we're headed. Before we open it up for questions, I do want to just talk about one quick thing. And that is actually what I mentioned at the beginning is CoCoRaHS. So yeah, we'll go here. So when we talk about really heavy rain was really the inspiration for CoCoRaHS. So CoCoRaHS started at Colorado State University in Fort Collins, Colorado. That's where the Colorado State Climate Office is. There was a guy there named Nolan Deskin. He was there for probably almost 40 years. He just retired a couple of years ago. Anyway, Nolan was very passionate about rainfall and rain measurement. And he happened to be working there in 1997. 1997 is shown there on the screen. On the left is a map that shows the official observing rain gauges that were present in the area at the time. So that's a 24-hour total. So you got anywhere ranging from 0.74 inches of rain to 2.26 at the high point there. Those pictures on the right, yep, that's the acronym. So it stands for like Community Collaborative Rain and Hail Snow Observing Network. But in the chat, they spell out CoCoRaHS. But those pictures on the right side of your slide, those are from the same day. Does that look like more than 2 inches of rainfall fell on that day? I would probably shake my head yes. There was probably more than 2 rainfalls, knowing the Front Range of the Rockies and what that would look like. So yeah, it is a little ridiculous thinking that much rainfall, that little rainfall would cause that much damage in this location. So there's something missing. And so they've done some studies, there was some follow-up, and there were some individual private gauges that they got a hold of, and they started analyzing the data. And what it came out to was it should have looked something like that map there on the right, which shows a contour of 1 inch here on the outside, scaling up to most 9 to 10 inches right over Fort Collins. No gauge over here caught that. And so that led to the questions, man, we really need more gauges. And so there was another event in September 2013. So there was this big inspiration to get this volunteer network of people collecting rain observations every day in their backyards. They get a training on how to properly site the gauge. They get the gauge at a minimal cost from a supplier, and it's asked that people report precipitation observations every day or as often as they can. That event in 1997, because of that study from the Climate Center there on the right side of the screen that showed there's probably a lot more rain than we expect. Also, radar coverage isn't good here because it's in the mountains. Mountains block radar beams, so that wasn't a good option to detect the rain. So it was a really missed opportunity. But they figured that there's on average 8 to 10 inches of rain fell over Fort Collins, and it just happened to miss all the official gauges. An event similar in 2013 showed a similar setup, and that was what happened. They had this many more gauges. Most of these are CoCoRaHS gauges, not Colorado Mesonet sites. So these are volunteers providing this. But in 2013, they had a similar setup, and they see that, most of the area saw 2, 3 inches of rain, but there were some really isolated areas that saw 8 or 9 inches of rainfall, and they saw pretty similar response in flooding. That map on the left, there was a revised estimate for downtown Fort Collins. They raised to 6.17 inches for the official total. It's still likely an undercount, but this is one situation where citizens volunteering their time, just interested people, started contributing their efforts, and it really helped the scientific community verify a theory about a rare extreme event. Once they had this data that people collected, they were able to take a closer look at it. There's observers all over the country. We actually do have quite a few in Texas. If you're in Conroe, Walker, Montgomery County, I'm not sure if you're in our district or not. If you get in touch with me, I can point you to the correct coordinator. If you're in College Station, the coordinator is John, NG, our state climatologist. But if this is something that interests you, if you enjoy taking weather observations or interested in rainfall, just find this stuff kind of cool. That's how you spell CoCoRaHS. We're happy to talk with you and get you set up. Just showing the next slide. I can also, if folks want, I can email these slides or put a Google Drive link and send to Michael, and then folks can access these as well.
That'd be great.
Awesome. Okay, I'll email that to you after the talk. But now, so CoCoRaHS, you can go online to their website and see a map every day of all these observations that were reported the day before or that morning as they come in. So that's just one effort that some interested people in the climate community and in the regular community got together and took observations, and it has made a difference. One local example of this making a difference was out near New Braunfels in Texas. You'll notice on the radar there, that lower left inset, you can't really see it. There was this persistent area of rainfall, and it looked like it wasn't moving. And the Weather Service office out there was getting calls like, is that real? Like, is it raining over there? It just hasn't moved for a few hours. And they're like, no, it's a problem with the radar. Well, every gauge around that spot saw almost nothing, but that one spot where it's circled on the map there saw 7.12 inches over May 6th. So that little cell that they thought was an artifact was not. The observer noted that all but 2/100 of that fell between 3:30 and 5:30 p.m. So that was just one of those really lucky situations in this case where we had a gauge underneath what we thought was a radar artifact, and it turned out to be real rainfall. So those are just some, not maybe as impactful as the Fort Collins one, but still pretty major contribution that helped the Weather Service out a lot there on validating their radar imagery. So that's the type of thing that we take CoCoRaHS data in the community to actually use it. So if folks are interested in getting involved with that, reach out to me or John, and or the contact information you can find on that site, and we'll be happy to talk with you. Just some examples of where this data is being used. The National Weather Service use it. Their hydrologists at the River Forecast Center use it. County level emergency managers use quite a bit of it, as well as city utilities, USDA, and the list goes on. So a lot of people use this data. So I know I'm talking about it like it's, hey, somebody said they posted their 2000th record recently. Thank you for doing that. That's awesome. Yeah, so not trying to talk this program up too much, but I think it's a really great thing. I spent years looking at rainfall patterns. So anybody who's willing to take the time to collect precipitation data is helping us out a lot. Let me just go forward one more slide. This is just kind of an example of the station density currently around Houston, in the Brazos up towards DFW as of 2021. We've added some more stations since then, but that's kind of what the station density in our region looks like currently. With that, I'm just going to go to the end here so we have some time to chat. But just to summarize it all up, as John likes to say, Texas climate is challenging, but we've been getting used to it. So what we're seeing with variability now adds a unique wrinkle to the puzzle. So you can reach out to me through my email there. If you also go to the SRCC website, you can find my phone number, also our main office number. We do have social media accounts, even though we're not as good about updating them as we should be. But you can find those on X or Facebook or Instagram or Blue Sky at those handles. We also do have a website for the State Climate Office at climatetexas.tamu.edu. And the Southern Regional Climate Center, you can find a lot of our tools there at srcc.tamu.edu. But with that, thanks so much, everybody. And I know I talked a lot, but happy to answer any questions that you guys have.
Any questions for Dr. Bali? I know we're kind of up against the time, but getting lots of thank yous, if you can see in there, and
I see that.
I'll add to that. I'll go ahead and do the announcements. If you have a question, put it in the chat, and we'll keep watching.
Sure.
That's
Yeah,
there.
I'll hang out till you guys are done meeting, and yep, then I'll hop
Okay.
off. But thanks again for having me. I really love doing these talks, and happy to come back anytime.
Thank you. So just a few quick announcements if people hold on. First, all of the interns, you should have gotten an email that's an invitation to Slack, which is a collaboration tool that we have access to. And there are a couple in particular channels that Ashley, who's spearheading the effort on that, was talking about. One is the hashtag 2025-class, and the other is hashtag Montgomery-pollinator-garden. So not required, but certainly it might help you a lot in looking for information, finding information, having your peers list information for you as well as your mentors. So look at that, look for that email, and sign up. It doesn't cost anything. That's even better. As always, I'm no nag about this. Please enter your hours in VMS. Because if they're not in VMS, it never happened. At least that's the way a lot of people view it. So please do that. If you have any issues associated with doing that, just let one of us know. Let anybody on the training team know. We can help you fix whatever the issue is. So our chapter meeting is this coming week on the Wednesday the 12th. It is going to be at the AgriLife building, which we have been to before in Conroe. We've had classes there, so you know where it is. It's from 6 to 7:30. There's information in the newsletter that just came out. If you subscribe to the newsletter, which I would strongly recommend that you do. Our next class is not until the 22nd of March. It'll be at the Montgomery College campus of Sam Houston State on 242. We have been there before. At 8 o'clock, it's a forest ecology presentation, followed by at 10 o'clock by a presentation on the red-cockaded woodpecker. And then we will reconvene the class for those that can at the W.G. Jones Forest, which is just a few minutes away, and do a walk and look at the habitat of the red-cockaded woodpecker and maybe even get to see one. So I think those are all of the announcements. If I've forgotten any, please let me know. Look down here get down here to the end. I don't see any others. Thank you, sir. We appreciate it. Have a good evening.
All right. Thank you all again. If
you soon.
anybody has any questions or just wants to chat, feel free to reach out.
Appreciate it. Thanks. Bye.